In this video, I'm going to go through an example of doing a calculation with unbalanced torques. So I have a problem here. In an Atwood machine, a block of mass M1 and a less massive block of mass M2 are connected by a string. I'm going to go ahead and make a note right away that M1 is greater than M2. And I can see those are already labeled. So this is information I'm not going to have to keep track of. So I'm just going to cross that out. They're connected by a string that passes over a pulley of mass M, radius R, and rotational inertia I. I'm going to go ahead and add that information to my diagram. So the radius goes from the center of the pulley out to the edge. That's R, and we also know this has a mass M and a rotational inertia I. I'm going to go ahead and cross that information out as well because I no longer have to pay attention to it in the text. And in fact, that entire setup in the first sentence I now have accounted for in my diagram. So I don't really need to pay attention to any of that anymore. So from there, I'm going to work on part A. What is the angular acceleration of the pulley? So to find that, I'm going to have to use this second law for rotation, where angular acceleration equals net torque over rotational inertia. So the next thing I'm going to do is I know that each of these masses applies a torque to this pulley. I like to add a little note about which way that torque is. Mass 2 is going to be applying a counterclockwise torque. As it exerts its force on the pulley, it's pulling downward, which is going to, or actually clockwise. It's going to cause that pulley to rotate clockwise. Mass 1 is exerting a torque in the other direction. As it pulls down, it's going to be trying to rotate the pulley counterclockwise, so in the opposite direction. Now, I know that each of these torques is going to be equal to the force of gravity on that block times its distance from the center of the pulley. So mass 1 is going to exert a torque of M1 times little g times R. Mass 2 is going to do something really similar, except it's just going to be mass 2 instead of mass 1. Now the next thing I'm going to pay attention to is that mass 1 is greater than mass 2. That means it's going to exert a greater torque. So I'm going to go ahead and treat the direction that mass 1 is trying to cause that pulley to rotate as my positive direction. So that means my net torque is going to be the torque from mass 1 minus the torque from mass 2. So my net torque is M1 G times R minus M2 G times R. And if I want, I can make this look a little bit simpler. I can pull that G times R, or again, G is the strength of the gravitational field, so that 10 meters per second squared, or 10 newtons per kilogram. And I'll do M1 minus M2 in parentheses. And once I've got this, all I have to do is go back and plug it into that second law for rotation to get that my angular acceleration is equal to the net torque, which I have just above, divided by the rotational inertia. And that right there would be my answer to part A. And so the way I started was really, really similar to how we started with balanced torque problems. I skipped actually drawing it, but I was essentially looking at what are the forces that are applying torques on here. And so I didn't sketch an extended free body diagram, but I was still thinking that through. And then I figured out which way is each of those forces applying a torque. I figured out how big those torques are, and then I plugged them in to that Newton's second law for rotation. Now, part B is actually going back to earlier in the year with unbalanced forces. I figured I'd leave that part of the problem in since it's a good review. Now we're looking for the acceleration of the blocks. So I'm going to have to go through Newton's second law from earlier this year, where acceleration is net force over mass, where that mass is the mass of the whole system. So what I decided to do is put this entire thing into my system. So I said the mass of my system is the mass of block 1 plus the mass of block 2. Now the reason I did not include the pulley's mass here is that pulley is attached to an axle, so it's not actually accelerating vertically. It's fixed in place. And so the force of gravity on the pulley is balanced by the force that axle is using to support it. So I'm only going to worry about the mass of those two blocks. Now for the net force, I figured since the force of gravity on the pulley is balanced by the force of the axle on the pulley, the only two forces I have to worry about are the force of gravity on mass 1 and the force of gravity on mass 2. So I went back to that idea that the force of gravity is the mass times little g, that's strength of the gravitational field. So the net force on my system is m1 times g minus m2 times g, and I decided to go ahead and simplify that a little bit and pull the g out front. So I have g times m1 minus m2. And then the last thing I need to do is plug this in to Newton's second law. So I have acceleration equals g times m1 minus m2 divided by the total mass of my system, which is m1 plus m2. And because I have a minus on top, plus on the bottom, these are not going to cancel out, and that's as far as it simplifies, and I've got my answer to part B.